Okay, so let us take a quick recap of what we have been doing very quickly. I am just showing the previous slides. This is the one that filter structure which I begin with every day, and we are calculating this mean square error. Okay, epsilon square n is the variance of this mean square error. As I told you, we are not using the optimal weight, because in the steepest descent procedure we did not keep R and P, R matrix and P vector as it is, but we replace by some approximation, by some weird estimates. As a result, the filter even in steady state will not be converging exactly on the optimal weights, but will be dancing around that. So, therefore, E n will never be the optimal E n. So, if we find out the mean square value of E n, epsilon square n, we worked out it is equal to the minimum variance, epsilon square mean plus something. Epsilon square mean comes to what? When you put the optimal weight, the corresponding error E o n, the variance of that is epsilon square mean, but plus some terms. What are these terms? If you have the input autocorrelation matrix, this you decompose it like this: T D T transpose. T consists of the orthonormal eigenvectors, D consists of the eigenvalues which are all real and positive. T is a unitary matrix. Then this eigenvalues lambdas, they figure here. And what are what is K I prime? Well, delta n we defined as the deviation of the weight vector from the optimal one. This is a deviation. Okay. The deviation will only fluctuate around 0, okay, mean 0, because the deviation, W n is fluctuating around W up in the steady state, but it will never be exactly equal to 0 always. And this delta n, if you take the auto covariance matrix or auto correlation matrix, either way they are same, because mean is 0, you call it K n. Then from K n we get K prime n this way, that from delta n, if you find delta prime n as T transpose is coming from the autocorrelation matrix R. So, T transpose delta n, then delta prime n has a covariance matrix equal to K prime n, which is related to K n by this. And so, from delta n we obtain delta prime n, from the covariance matrix of delta prime n is K prime n, and diagonal entries of that figured in this expression. Simultaneously, we also derived x prime n from x n by T transpose x n, and x prime n is then vector which has got autocorrelation matrix, which is a diagonal matrix given by the eigenvalues. These are very standard stuff discussed time and again. So, no need to go into that. Then what I said is this, that this quantity which depends on K I prime n, we must make sure that with time n, as n tends to infinity, this term remains under bound, it does not grow, because if it grows then the error is unbounded and it will be, the whole algorithm will be destroyed. So, it has to be some finite quantity under our control. In fact, the quantity also can be then made lower by some appropriate parameters, but this should be first bounded, that is, as n tends to infinity, this quantity K I prime n must not go to infinity, it must be bounded up to some finite value. That value should be under our control using some lambda or maybe mu and all that, with which we will play with that. Okay. So, therefore, we have to see the behavior of this K I prime n, which is a diagonal element of K prime n. But then I said that instead of taking only the diagonal elements of K prime n, let us take K prime n, let us see how this matrix evolves in time. So, we developed we are trying to develop a recursive equation for K prime n. Very quickly, the steps were like this. We know delta n equal to this. Okay. So, we want to find out delta n plus 1 in terms of delta n. Delta n plus 1 was, we know W n plus 1 is the LMS equation. So, if you subtract W opt from this side and this side, you get delta n plus 1, delta n here, mu x n. E n we expand d n minus x transpose W n, and W n is again W of plus delta, put that back here. So, you get this, but we are not interested in delta, we are interested in delta prime. So, you have to multiply both sides by T transpose this, you get this expression. Okay. Delta n, T transpose delta n is delta prime, therefore, delta n is T delta prime. So, you put that here T delta prime into delta, T transpose on this side, T transpose here. Okay. And T transpose is a unitary matrix, T transpose I t was equal to I, T transpose x n was x prime n, x transpose t, that is x prime transpose. Okay. So, this is how you got it. This is all standard stuff, no question of explaining further, I am just linking up, that is all. Okay. This is the term, this is your K prime. So, this is your delta prime n plus 1. So, what is K prime n plus 1? Is the covariance matrix for this vector. So, E of this. this matrix I want to develop a recursive relation for this matrix. So, k prime n plus 1, how it comes from k prime n. Therefore, what we did then is this. We took delta prime n plus 1 as it is, as obtained by the equation, we wrote it entirely, no parenthesis, nothing, broke it up, and you take delta transpose of that, because after all what is k prime n plus 1, that is nothing but this delta prime n plus 1 into its transpose, then expected value, isn't it. So, delta prime n plus 1 has got 3 terms, transpose also will have 3 terms, we will have 3 into 3 this multiplication, we will have 9 terms, that is very elaborate. Okay. So, 3 terms, here all transposed, and then we did cross multiplication and analyzed, and there we found that we wrote down all the component, this and this was giving rise to k prime n, you have to multiply and then take e operator on that, this and this was giving rise to k prime n, this we worked out, this term was giving rise to 0, no, this term was giving rise to mu d k prime n, because this into because of the independence assumption delta prime and x prime they are independent. So, E will work on this, E will work on this. So, that is why D is the correlation matrix for x prime. So, D will come, delta prime transpose will give rise to k prime n, that was coming, this was giving rise to 0. Again, because of independence assumption, this could be separated out from this, and this is orthogonal to the elements of this, that is why this is 0. So, this term was 0. So, this is one term, this is one term, wherever I get non-zero term I have to collect them. So, I am just putting a tick, not here. One more term. So, 3 terms done, this, next is this, okay. This one again is not very difficult, delta prime transpose, x prime transpose, again they are separable. So, this will give rise to k prime, this will give rise to d, that is why this is, and mu before that minus sign. So, minus mu k prime and d, previously it was d k prime n, it is k prime n d. Okay. Then this term minus plus mu square, and this is a huge term, that time I said I have to evaluate it later, which I will do today. Remember this term x prime transpose, transpose, delta prime transpose, and again x prime transpose. Okay. This I have to work out separately today, to be done later I said. This cross term was x prime E0 is scalar, so you can put it behind. So, in the front E0 x prime and then delta prime transpose x prime there I made the assumption that dn and all the elements of x n they are jointly Gaussian. And how do you obtain E0 n and x prime n? E0 n is nothing but dn minus w of transpose x n, and what is x prime n? T transpose x n, the 0 is here, 0 will take care of dn. Okay. So, this is a matrix working on this, giving you this. So, any linear operator, this matrix working on a Gaussian vector gives you a Gaussian vector. Therefore, these elements also are Gaussian, but since they are Gaussian and E0 n is orthogonal to all the, this uncorrelated to all the elements that of x prime n, that means this is also statistically independent, because under Gaussian uncorrelated means independent and vice versa. So, therefore, E0 n is statistically independent of this. In this entire expression, E0 n can be separated out, because it was already by independence assumption independent of delta prime, and now we have made it independent of x prime. So, this is independent of the entire quantity on the right, and now E of this and E of this is 0, because what is E O n after all? dn minus w of transpose x n, x n has 0 mean, dn has 0 mean. So, this has 0 mean. So, this gives rise to 0. Okay. So, no tick here. And what are the other terms? By the same logic, this also, this was becoming 0. You can see this, isn't it? This cross term is 0, because after all these two can be separable from this, and this is orthogonal to the elements here. This and this also will give rise to 0, because E0 n you can take out, it is independent of all the other quantities. So, this cross terms will become 0, only this minus plus mu square E0 square n, which is scalar term x prime n x prime transpose. That is why I said those two terms are 0 and the third term is non-zero, E 0 square x prime transpose, okay. And E 0 is independent of this, therefore, E 0 square is independent of these terms. If x and y are statistically independent, x square and y square also statistically independent. So, this is separate, which gives rise to epsilon square b because of optimal error, and this gives rise to the correlation matrix of that, which is D. So, this is one term. So, I have picked up the terms, now I have to evaluate the one which we did not evaluate last time. So, let us start with that. What was the term? That was okay. You will agree I can apply E over this inside, because this is separable from this and this side. After all, this will be a matrix, this will be a matrix, this will be a matrix, all cross terms will be a product matrix. On that, if you apply E, in those product terms, there will be terms coming from x prime n and this side and this side. So, E can be, when E works on that, see, if you take the entire matrix, the resulting product matrix, each element of that will be a summation of many product terms, scalar products. Okay. There, if you apply E on each, you can separate out components coming from this and components coming from them. Okay. Can you see this? So, I can apply E inside, or do we have to talk on this further? You have one matrix, so you will have some two terms, say some terms multiplied here, okay, and some terms. So, actually the product matrix in each term will be, each term of the resulting product matrix will be summation of terms, elements, summation, because after all if you take this product, and any matrix into matrix is what? This into this plus this into this, that plus is there, summation, again another matrix. So, when you do this matrix product, each term of the resulting matrix is summation of many terms, but each term in that summation is again a product of several scalar terms, scalar ones coming from this side, from this side, from this side. There on each, if you apply E, you can separate out, you can apply E over the terms coming from this separately and E over the terms coming from this separately, and you get a resulting expression that is following this method. But if I beforehand apply E over this only, I still get a matrix of those terms which I would have got by applying E after this entire expression, okay. And then you multiply and then reapply E again, you will get the same thing. I think you can now you can visualize it. Otherwise, try a 2 by 2 matrix if you want. If you apply E over this entire quantity and this remains as it is, what is this quantity? This is equal to not D, this is K prime n. This entire expression, suppose I call a matrix C n. It is of all not random, because E has been applied already. So, what is C n? C n is E of this transpose K prime n, this transpose. Now, look at this. This x prime transpose is a row vector, K prime n is a matrix, and x prime n this much is a column vector. So, matrix into column vector is a column vector pre-multiplied by a row vector. So, that will be a scalar, this much is a scalar. Huh? No, I am not talking transpose, this much is a scalar, isn't it? So, scalar can be pulled out also. Suppose the scalar value is 2, so 2 can be pulled out, not out means not out of E, I mean can be kept in the front, then x prime transpose, a scalar term, isn't it? So, please identify this is scalar, so I can. So, if you take this element only, this is a scalar, this scalar term, let us evaluate the scalar term. What is the scalar term? I will apply E later. Okay, what is the scalar term? This is a matrix. This matrix will multiply this vector, so we will get a vector. Ith element of this vector, ith element of that vector, multiply it and sum for all I, isn't it? Ith element of this product vector is what? If you take the ith row of k prime n, first column first element, second column second element, third column third element, like that go on multiplying, add. That will give you the ith element of this product vector, that times ith element of this row vector, multiply and go on summing it for all the i's, isn't it? So, that means ith element of this guy is n minus I. You remember the definition of x n vector, x n minus 1, x n minus 2 up to x n minus capital N. So, is x prime n. So, x prime n minus I, and then you have got this guy k prime I j. This is a matrix. Ith element of this is denoted by this times jth entry, isn't it? Ith row jth entry into jth entry here. This must be pretty simple. You hold I fixed, means ith row, go on sweeping j. As j moves, j equal to 0, j equal to all the columns of ith row, multiplying the different elements of the vector. So, it is a row into column, isn't it? So, this product vector you get ith element and ith element here, multiply and sum it for all the i's. So, this will be a scalar term. Instead of having the sum here, I can put the sum here also. Instead of it here, I can now together. Okay. Normally, DSP will do the other way, double summation with an interchange summation, all that, but here I am doing going backward, just to keep like this, fine. But this was only this part with E here, of course, but before that I have got a column vector, a row vector. This is a scalar, this entire thing is scalar. You can call it k or alpha, so you can call it even alpha and say. So, this is the matrix. What is the typical element? Say L m, element of this matrix, that is E column vector, row vector, column vector x prime, row vector x prime transpose, and multiplied by whatever is the matrix, that is multiplied by scalar alpha. Alpha you forget for the time being. What is the Lmth element? So, Lth entry of this vector times mth entry of this, you understand? This is a column vector, this is a column vector, okay. Column vector versus row vector, this is the thing. So, first this into this, this into this, this into like that, first row, second element into first, second like the second row. So, Lth element into 0, 1, 2 like that. So, I am interested in mth. So, mth. So, mth guy, Lth guy, isn't it? So, here will be x prime n minus L, Lth guy of this vector, and on the right side will be x prime n minus m, right. But now this is a scalar term, after all this is a scalar element. So, whether you put the term before or inside summation, all it does not matter. Okay. So, I apply E, E also has to be there, but E can be pushed inside the summation. These were already present. From this side another term, this x prime n minus L is coming, Lth guy of this vector, that I am pushing in, then these two. Remember, k prime is not a random quantity, k prime is correlation matrix, already E was applied to obtain the correlation matrix, isn't it? So, this is not random. this will go out. N minus j and the mth fellow here, that also will come in. All this multiplied by this k I j prime n. This is the thing. This quantity pre-multiply by Lth fellow here, that is x prime n minus L, post multiply by x prime n minus L. But what is pre and post multiplication? They are all scalars. Scalar terms, scalar terms, scalar terms. You can push the two scalars inside here and here, and then apply E over it. So, for x prime terms, they are the random numbers, random variables, E over that. This is not random, so it goes outside E, that is all, and summed as before. Please see that you understand some statistical analysis. Again, I told you one purpose of this course, one main purpose is to make you conversant with this kind of statistical analysis procedure, so that you yourself can study other literature or do analysis on your own. Okay. But these are the things which come very come often in communication control and signal processing. This kind of analysis. Okay. Now I have got this terrible quantity. So if it is only a product of 2, I know what it is. If it is 1, I know, but it is a product of 4. There is a big problem. It is called fourth order moment. Correlation is called second order moment, mean first order, the fourth order. Again, so we will make use of that Gaussian assumption, and under Gaussian we know already that they are jointly Gaussian, and under jointly Gaussian thing, there are some results on this kind of fourth order moments. So I will not prove that. If you are interested, you can see my lectures, NPTEL lectures on probability random variable. These are derived, not very difficult. Okay, I will only quote you a result first from probability and statistics on expected value of this kind of product of 4 terms, which are jointly Gaussian. So that is like this, if suppose you have got 4 terms, x1, x2, x3, x4. Forget all those, just new variables x1, x2, x3, x4. And suppose they are jointly Gaussian. Jointly Gaussian. Then if you have, I do not remember whether they require to be have 0 mean or not, but to be required, right. But to be on the safe side, let us assume 0 mean, because that does not do any harm to us. We already are assuming 0 mean cases for all the data, is not it. So, if it is required, I am not sure, I have to check, though I do not remember. Then under this joint Gaussian assumption, this can be broken. First, you have one product x1, x2, it is like this, E x1, x2 multiplied by E x3, x4, just simple permutation, combination does x1, x2, x3, x4. Then there will be another term involving x1, x3, x2, x4. And another term x1, x4 multiplied by x2, x3, that is E. These things you should always remember, because they help you in you just you are suppose finding what should be a difficult spot in this thing, in this analysis. You then if you know this, okay, you immediately assume that Gaussian thing and things become simple. These are common tricks, techniques applied in all these analysis procedures. Okay. So now I have got this one thing. You see, it is very easy to remember. First 2, second 2, and then first and third, second and fourth, and then first and fourth, second and third. And but what is the E is working on only a product, second order. Second order is no problem for me. This works for Gaussian case. I do not know with 0 mean, but let us assume that since we are dealing with 0 mean cases, it will in any case work. Okay. So this I will apply here. After all, these 4 terms are jointly Gaussian. Now remember, x prime n, please see one thing, x prime n was what? T transpose x n, and what was the implication? If you take E of vector into this transpose correlation matrix, what was that thing? That was diagonal D. Okay. That is, this vector is such that any 2 terms, they are uncorrelated, their cross terms, their correlation is 0, only individual terms of the variances given by the eigenvalues. You understand this product, na? this diagonal matrix. So, cross terms ith guy, lth guy from here, their correlation is 0. Each guy has got some variance given by the eigenvalues, right. So, that means E of in general, if I take say any ith fellow here or say any rth fellow n minus r, and say I take anybody say k n minus k, rth fellow, kth fellow, that will be what? If r and k equal to 1, same, r and k are same, then only it will have some value, otherwise 0. So, firstly there will be a delta r minus k or k minus, it does not matter, and when r equal to k, it should be the variance of x prime n minus r or n minus k, they are same. That will be given by lambda rth fellow, or lambda r or lambda k both are same. So, you have to keep once lambda r. Lambdas are positive and real. Okay? Please remember this. This will help us in this analysis very much, and I have got only those cross terms, right. So, this outer sum remain as it is. Permit me to skip some step, because you already know this result. I will write directly E over this product into E over this product. Okay. E over this product will be what? Delta L minus I or delta I minus L, delta I minus L, and lambda, you can say I or L, does not matter. Okay. Say lambda I, delta I minus L from these two, multiplied by E of these two. You remember that expansion na, for Gaussian E of this first and second into E of second, third and fourth. Third and fourth will give rise to lambda j delta j minus m. So, lambda j delta or lambda j delta j minus m. Then next is first and third, second and fourth. First and third, now you can very easily see. First and third would give rise to what? Lambda j delta j minus L and delta I minus m lambda I between third and fourth. And there is one more term, first and fourth, second and third. First and fourth will give rise to lambda L delta L minus m, and first, second and third will give rise to say lambda I delta I minus j. Okay. And this entire thing summed over I equal to 0 to n, j equal to 0 to n, and this multiplied by this quantity k I j prime n. This is what I am. So, let us handle this term separately. It is not very difficult, looks clumsy, because of the delta, beauty of delta, you know, things will become very simple very soon. Start with the first term. Just look at L and M are fixed by you from outside. L and M are your choice, they are not variable. You have fixed up, you want to find out this particular entry for a particular choice of L and M. But I and J are running in this summation. So, only when I equal to L and J equal to M, it will have a non-zero value, right. That means, this will give rise to what? Lambda L, lambda M, k prime L M n. That means, one term will be, can you see this? No, you can see this line, right. So, one term will be lambda L lambda M k prime L M n, fine. I equal to L, j equal to M. Here also L and M are your choice, but j and I are changing. So, only when j equal to L and I equal to M, you get non-zero value. So, that will give rise to again lambda L lambda M. K prime ML, but K prime is symmetric. First let me write ML, but this is equal to, let me write also that K prime, this is equal to K prime. Essentially these two quantities are same, lambda L lambda M and K prime L M N, because K prime is a symmetric matrix, correlation matrix after all. Third guy is more interesting. Third guy has this problem. L and M are your choice. Only I and J are. So, L and M can be brought outside the summation. They are not there. For your particular choice of L and M, it will have some value, either 0 or 1. If you have chosen L equal to M, 1, so you understand that this will be, this term will give rise to a, I mean, it will amount to a diagonal matrix in some way. Okay. If these other terms were not there, only this, then this would have become a diagonal matrix, but only for L equal to M, this will have non-zero value, otherwise, but I have got other terms also. So, this will contribute to a diagonal matrix, right. So, anyway, delta L minus M I bring outside, lambda L I can bring outside. Summation lambda I, not summation, there is double summation, you see, I equal to 0 to n, j equal to 0 to n, lambda I delta I minus j. For each I, j is changing, but in this summation, I will take only those values for which j equal to I. So, you pick up one I, and then as j moves from 0 to n, only j equal to that I has to be taken, and then it becomes 1. And how many such cases will come? N cases only, isn't it? So, it simply becomes lambda I k I, not I j. Do not forget this guy, this is very important person. My botheration is about this fellow, na? So you cannot throw away this. Is this fine? Okay, so this is a particular element of the resulting matrix C. Looking at this, can I construct the entire matrix? These are all the scalar terms. First, look at this guy. I have got this and this same, so twice this. No point in handling this separately. Twice this. What is this? For your sake, let me work out on another piece of paper. Say, what is this quantity? You have got, suppose k prime n. If you have a vector lambda 0, lambda 1 dot 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 lambda n, I call it lambda vector transpose, and if you have got lambda vector lambda 0, lambda 1 dot dot lambda n, sorry, just a minute, no, this is not this, just a minute. Suppose you have got k prime n, you got the vector d, you know the diagonal matrix consisting of the eigenvalues, and here also. So, you get a matrix only 0 0 0 0 d, matrix into matrix into matrix. What is the mth element of that matrix? You can see easily. First, consider this. Multiplying two matrices means, I told you, do not multiply matrices like a schoolboy. Okay. Multiply by linearly combining the columns. Now, lambda 0 and all zeros. Lambda 0 times first column, that will come up. Lambda 1 times, because other zeros will multiply other columns, no contribution, isn't it? So, whenever you do this kind of multiplication, lambda 0 times first column, lambda 1 times second column, dot dot dot, lambda n times last column. Isn't it? I am interested in, suppose, the mth element. Anyway, this will give rise to again the same d into, let me write out, lambda 0 times a first column, 0th column, lambda 1 second column, dot dot dot, lambda n. These are column vectors of this matrix, Cn, and now multiplying by D. If you multiply by D, pre-multiplication, that time what I told you, you have to linearly combine the rows by the elements of the, like you are combining the columns by the elements of this. If you have this row, lambda 0 into first row, the next element into second row, next element into third row, and combine, isn't it? So, what will that give rise to? Lambda 0 times, this is a matrix, various rows are there, lambda 0 times first row, lambda 1 times second row, okay. Lambda 2, that will be the final matrix. What is the L for the Lth row of the final matrix? Lambda L will come from this side, lambda L times Lth, lambda L times Lth row here. These are columns, these are column vectors, and then you are forming rows. First row times lambda 0, other rows will multiply by the 0, 0, 0, no contribution. So, lambda 0 times first row will be the final first row, lambda 1 times the second row will be the final second row. I am interested in the Lth row mth element in the final matrix. So, Lth row will be what? Lambda L times Lth row here, that will be the final Lth row, and in that Lth row I am interested in the mth element. In the mth element will be what? Mth column. So, lambda m, lambda n times whatever value it had, isn't it? So, that means this will give rise to lambda L, lambda m times whatever value it had, this matrix set at the LMth position, that is lambda m C m, lambda L, lambda m gone. This is a column vector, you are now looking at the Lth thing. So, L mth element of this matrix, after the columns are of this matrix only, C 0, C 1 dot dot dot, here from only they come, lambda L, lambda m done. Okay. I am looking at this column because it is mth and Lth row of that. So, Lth row and mth column of what does it mean? The LMth element of this matrix, yes, isn't it? I don't know, I can, I mean, just by sheer practice, you should reach a stage where you can see, I mean, you can directly write down, you do not have to really do this inspection, like I can do it today. It is not very difficult, these things come very easily, you can easily quickly write down the matrices. Just practice. There is absolutely nothing conceptual here, it is just a quick practice. I can easily see who is post multiplying, what is post multiplying, how will row affect, how will the columns be affected. Since you are not used to, you have to do this visual inspection and all that. So, this is your k prime L, that is what you had here, lambda L, lambda m, this. That means, when you consider the matrix, not just the element, the entire matrix, this will be D, this is D k prime n D, and twice of that, because these two are same, twice D k prime n D plus you have got things here. This is not difficult. Consider this. This is a scalar. This summation is a scalar independent of L and M. You are finding out LMth element, this is just a scalar independent of L and M, some quantity, say 2, 3, 4, whatever, keep it aside. You have got only this delta, so it is not very easy. It will contribute to what? A matrix where only diagonal elements are non-zero, isn't it? LMth element is given by this, it will give rise to a matrix where LMth element is given by this. So, that means it will give rise to a what? It will give rise to a diagonal matrix, where, but multiplied by lambda, actually it will be D, isn't it? Because L and M have to be same, and there the element is, so this is 1, L and M, only when L and M equal to 1 same, then it is 1 multiplied by lambda L. So, L Lth element is lambda L, that means this is a diagonal matrix, this will give rise to D, and this will give rise to what? Very good, trace of either way. you can write d k prime n. I told you trace of a b and trace of b are same, but you can put the d here also. Can you see this? D k prime n, after all k prime n has those rows, first row multiplied by lambda 0, second row multiplied by lambda 1 dot dot dot, that is all, is not it? And then you take the trace. So, first row multiplied by lambda 0 means, so that first diagonal element is multiplied by lambda 0, second diagonal element multiplied by lambda 1, and that is what you have here, na? Lambda 0 first diagonal element, lambda 1 second diagonal element, like that of the matrix. So, this simply trace. So, now let us collect the terms quickly. Because there are many 0 terms. So, k prime n plus 1, we are finding out how the matrix evolves recursively. There are so many terms, many are 0, and I put tick against those terms, tick marked. So, there was k prime n. So, k prime n, then minus mu d k prime n, and just a minute. D k prime n then this term d k prime n and k prime n d, both with mu and minus sign. Others are zeros. And then I said to be done later, this one and this one, last one. So, the one which I said to be done later, now I know what it is. There was a mu square. So, I have to use that mu square also. So, plus mu square into this entire thing. This entire thing I call Cn. Cn was this, isn't it? So, mu square into these terms. So, twice mu square d k prime n d plus mu square d trace and that last term this last term mu square epsilon square mean d. This might look bit frightening, but again with this all this become very simple. Now, remember this is how I am seeing the dynamics of the matrix, but in that error analysis it is not the matrix entirely that was of interest to us, it was only the diagonal elements, isn't it? You remember, just for your this thing, we had epsilon square n was epsilon square mean, but there was an extra term. What was the extra term? Lambda I k I prime n. So, I am not interested in all the terms, I am only interested in that is this is becomes this plus, if you can call a vector, lambda transpose into, I am giving some definition now. This is lower k, I am defining a vector now, it is just notation k prime n, where lambda vector is lambda 0, lambda 1 dot dot lambda n, this notation, and this k prime n. If you basically what is happening, if you take all the diagonal entries, put them in a vector form.
So, that itself is the trace.
No, do not bring trace here now. This is if I take a vector, because I am only interested about trace means again I have to bring the matrix.
So, then we can directly combine the last two terms and that is epsilon square as
Which one?
mu square d common,
Huh?
then we will get epsilon square n in the last two terms from the
I am not dealing with this now. Here only. Here this I am just writing in a compact form. I am defining a lambda vector like that. What I am doing, the diagonal entries I am picking up from this matrix, picking up and then putting them in a vector form. That vector I am calling out lowercase k prime n. So, k prime n is nothing but capital K prime 0 n, capital K prime 1 n dot capital K prime n. Basically, what this K prime, I am interested in the diagonal matrix of this guy, of this vector. So, I am taking all the diagonal entries 0 0 1 1 2 2 3 3 like that, putting in a vector form, and corresponding eigenvalues also I am writing lambda 0 lambda 1, and now you see, can I not write like this, lambda 0 into this fellow, lambda 1 into second fellow, that is what you have here, lambda 0 into k 0 0 prime n, lambda 1 into, I am just writing in a vector form, this is nothing conceptual, it is just notation, some compact notation. I do not want to get rid of the summation and all. Okay. So, what is the quantity of interest? Either the diagonal entries as written here or this vector, both same, this consists of only these entries only, not the entire matrix is of our interest. I found out the dynamics of the matrix, but essentially other entries of the matrix do not matter to us, only this vector. So, therefore, why not develop from this by very simple steps a similar dynamic equation for the vector only, not on all the elements of this non diagonal elements of the matrix, only for the diagonal elements, just diagonal elements are put in a vector form. If you do that, it is not very difficult. You take a particular diagonal entry here, k prime I n scalar. I will do for a particular I and then put them in a vector form. So, that will give me the dynamics for this vector. Sorry, this is not n, this is n plus 1. This is k prime I matrix. So, I am bothered about the I comma ith element of the left hand side and therefore, the right hand side. I comma ith element of this is again this minus mu. Now, tell me what it is. I comma ith element of d into k prime n. Lambda 0 first row, lambda 1 first, or say lambda 0 0th row, lambda 1 first row, lambda 2 second row dot dot. So, lambda I ith row, and in that ith row ith column. So, lambda I times k prime I. This side also will get the same thing, because you are hitting at the diagonal entry, lambda 0 0th column, lambda 1 second first column like that, lambda I ith column. See that ith column all that is multiplied by lambda I, and now you go to the ith row of that second lambda I. So, you are getting basically twice. I hope by this you become somewhat expert in matrix manipulations, this kind of things, some statistical analysis as you go through this. 2 mu, what we had here, lambda I. So, this quantity is coming back again, this quantity. Then here also it will come. Please tell me what it will come here. 2 mu square k prime n, first post multiply by d. Okay, all the first column 0th column lambda 0, first column multiplied by lambda 1 dot dot dot, ith column multiplied by lambda I. Lambda is square, isn't it? Should that be lambda is square? Just a minute. Yes, 2 mu square lambda is square. This morning I worked it out actually. 2 mu square lambda is square, same quantity. Okay. This much I put separately. They involve this k I prime n. Here mu square, this is a scalar, and d, my God. So, lambda I only, this is the matrix, the scalar. So, I lambda I times this, and this trace is what? Summation lambda I k prime I n, as I did before, and after that this quantity mu square epsilon mean lambda I. Okay. From here, sorry, okay, epsilon, okay, by notation, yes, square is part of the notation, fine. So, now you can take k I prime n common. So, you get 1 minus 2 mu lambda I plus 2 mu square lambda I square, is not it? This you can take common, k I prime n. So, 1 minus 2 mu lambda I plus 2 mu square lambda I square, this is a kind of constant, you can call it rho. So, now I am putting them in a vector form. So, what dynamics comes up, I will write that and call off today. Sorry.
Change the notation. Which otherwise it is messed up.
No, I am bringing this the lower case. That is why I am making it like this. The lower case means vector. I told you lower case underscore is vector, upper case underscore is matrix. That was the notation I told in the beginning. Upper case, no underscoring means scalar. Upper case later, capital A, capital B with underscore means matrix.
Lower case and upper case of k is very similar.
I am trying my best to make it like that, you see. This you must grant. Anyway, this will not occur very frequently, occur only for a while and go. This quantity 1 minus 2 mu lambda I plus 2 mu square, I have to quick to wind up. This quantity I call rho I, a scalar number. Oh my God, sorry. Here only I should have done this way. I do not think I have much time to I'll quickly write down the result. Plus rest. This quantity I will call rho I. Rho I. Okay, this is constant, but depends on I. So, that is why if you want to form the dynamics, here also this will give rise to what? I am putting them in a vector form. So, this also in vector form, a scalar times a vector, one element of the vector, scalar times another element of the vector. So, this will be again k prime n vector, but this is a diagonal matrix F. Can you see that? Some new diagonal matrix, or maybe what I do, I start from here in the next class, because they have given the alarm bell, there is no point in hurrying. In fact, very little is left after this. I will have a dynamic equation, and that equation will give us a stable solution. Under some conditions, that will give the stability for that error variance not to grow. Okay. So, I think I will just wind up in 10-15 minutes in the next class. We will start from this equation, mind you. So, I am still keeping this slide. Okay. Okay. Thank you very much.